you very much, Sylvain. Yes, I would like to remind you that there will be proceedings. So if you
probably
prepare more material
yes.
On your notes, maybe you can put this in the proceedings, right? So there's a second chance.
Yeah, that's sure.
Okay. So questions?
I'm just curious, is there any sense, like, what's the maximal gap you can get in spin liquids in sort of if all couplings of the order of 1? Because usually, as far as I understand, these gaps are very, very small.
I mean for real models, or yeah, this is why.
Yeah, for real models.
Yeah,
that's it's of the order of 1, or it's suppressed always. Because I remember there were like talks by Steve White. There's always argument whether it's spin liquid or phase which is broken, but with some, I don't know, very long effective lattice.
No, that's why I focused on some exact models or some general ideas classification. So we know that they exist, or this dimer model, etc. We have good numerics for that. But if you really take just a microscopic spin 1/2, people are very excited in the domain for J1, J2 square lattice, Kagome lattice, spin 1/2, and this is unsolved. So spin 1/2, indeed, so we have Philippe Le Cheminant, very early ED. What was the claim? Okay, I forgot, but probably the claim. Okay, some liquid. Then there was Steve White DMRG claiming it was a Z2 gapped. So they really measured the gap. It was 0.1, so it's not small, but okay. But now it was wrong because it was on cylinder. Then people say, oh, maybe it's a Dirac spin liquid. So Dirac is this U1 spin liquid. That can also live on the Kagome. So it's gapless. They were using some other tricks. Then maybe 6 months ago, there was a proposal for a chiral spin liquid, spontaneously breaking time reversal symmetry. Everything is possible. So for a given microscopic model, actually I didn't mention this, but it will be in my lecture notes. There's a very nice mathematical physics paper, which is undecidability of the gap by Curie, Perez Garcia, coworkers. So they map to a Turing problem, halting problem on the machine. So it's undecidable. So if I give you 2D local Hamiltonian spin, I give you the local H, can you tell me if there's a gap over the 1 or not? Undecidable. And not only they claim that, but they have an example where it's case A, so unique ground state on the gap up to linear size of 10 to the whatever you want, 10 to the 4, 10 to the 10. And then historic code, so 4 ground states on the gap, but very sharp. So something you can never see numerically. So there, I'm doing numerics, so I won't be confident in saying this is gapless. I think it's always very difficult. But they want to register.
So for these Kitaev type models, in particular, if you have like multi-body operators, I mean, the gap is 1, right?
Oh, yeah. That's why I say in this case, the gap is 1.
Yeah, and it's even actually, honestly, even for this B phase, you can, if you have a right type of perturbation, the gap is 1.
I think he was mentioning real microscopic spin 1/2, and then it's probably very small. In experiments, whether Kagome is a very nice, we have some materials, not a lot, but some. But people were debating from NMR measurement, do you have a gap or not? In principle, you see it in susceptibility, but you have impurities, you have Jablonski-Moria, okay. So devils is in the detail. And actually, that's why also I think the best platform are these maybe Rydberg arrays we'll hear later. You can realize Z2 phase, etc. But again, you have to be very, control the defect, etc. Very carefully.
Other questions? Maybe I can ask one. You mainly discussed the case of small spins, right? 1/2, 1.
Yes. Because we want
something interesting when you go to larger spins?
Actually, we want large quantum fluctuations. So this is a usual argument when you look at a commutator. If you normalize by S, I mean, the larger the spin, the more classical it is. So in fact,
yes. So then you can make the link with the classical models of the first part?
Maybe, but
It's a way to implement the classical models?
Usually it's more semi-classical phase, or it will become... it's not a good rule. Actually, the best route is SUN. That's why also SUN was started in quantum magnetism already 40 years ago, because it's a different route to have quantum fluctuations and to have more controllable analytical aspect. If you go to large N, you have saddle point, you can do something, but it's when you increase SU2 to SUN. if you increase the spin at SU2, it's more and more classical. It's not really interesting.
Okay.
This may be a related question. So I missed a bit the link between the first part of your talk about the degeneracy for classical systems and the quantum part.
Yeah, okay. So, I mean, they are slightly different topics because you don't ask exactly the same question, but maybe what I can answer is through this dimer model because maybe if I redraw, so essentially for dimer, if you are in, let's say, so maybe I can do, okay, 2D, 3D. So I can do 2D U1 when I'm bipartite lattice. So I have a Arche point which is critical. If I am in 3D, I'm also critical at the Arche point. So this would be V over T if I go to quantum. And then if I am 2D or 3D, that doesn't depend. If I am Z2, so if I am, let's say, triangular, non-bipartite, and this would be square, or diamond, or any bipartite lattice you like. If I am Z2, okay, then it's short range. So we know the classical case. Now we can, this is a natural way to do quantum fluctuations. I had some hopping or flip in the dimers. What we know from field theory argument or even Polyakov, so really high energy, very rigorous argument, it's a gauge theory. So gauge theory in 2D is always confining. So it's completely unstable. So this is gap, this is crystalline, or this is crystal. So it's confined. In the gauge theory, it's confined. So it's really only a fine-tuned point, but it's very unstable. So there's no really connection between quantum and classical. If you are 3D, then it's stable. Field theory tells you that gauge theory, 3D, blah, blah, blah. So there is a U1 liquid. So this U1 liquid, it has a photon mode, it looks like electromagnetism, and so that's why the spin ice were successful. There is classical spin ice in 3D, and quantum spin ice is probably the same phase. You can go from one to the other by adding quantum fluctuations. And now here, the connection in 2D would be, I told you about Vanier, etc. So you can compute, it's kind of Z2, dimer model, and again, it's stable. And this is a gapped Z2. So gapped Z2 and gapless U1, they can be understood starting from classical statmech, just by general argument. But 2D U1 is not working with dimer, so you need something more. This is Dirac spin liquid ID.
But so in the quantum case, you still have the extensive entropy?
No, actually, no. Yeah, that's why. So that was the comment. When I say gaps Z2, it was my picture that I have only 4 states on the torus and a gap. So this is why Anatoly said, yeah, Nernst's principle, we have many violations in classical, but never in quantum mechanics. Is it, Anatoly, is it, I mean, quantum mechanics, there's no example of extensive degeneracy ground state, I guess. Nernst was right, because world is quantum mechanics. Yeah, no, but just a comment.
Nernst was right, although he didn't know quantum mechanics.
Yes, that's correct.
Okay, so no more questions. Yes, it's time for the pause café. Okay, thank you again, Sylvain.